Hi, and welcome back to another LeetCode problem. We're looking at 2 to 7 basic calculator number 2. I think this is also a very classic problem. Yeah, let's just get into it. So we're given a string s, which represents an expression, and we are supposed to evaluate this expression and return its value. The integer division should truncate towards 0, so that means we're going to deal with a regular integer division in Python. You may assume that the given expression is always valid and all intermediate results will be in the range of a 32-bit number. You're not allowed to use any built-in functions which evaluates strings as mathematical expressions, such as the eval function. All right. Some constraints. So we are guaranteed to always get a valid mathematical expression. All the integers are non-negative integers in the range 0 to 32-bit number. The answer is guaranteed to fit also within a 32-bit number. Okay, so if it's a valid expression, and it contains the operators plus, minus, multiplication, and division. And if it's always a valid expression, then probably means we're not going to run into division by 0 problems. And we don't have any parentheses in our list of characters, right? Everything else is just going to be digits. And we are guaranteed to get at least one character in the expression s that we will receive. So yeah, let's have a look at these examples. So we can get, for example, this 3 plus 2 times 2, which is 4 plus 3 is 7. So operator precedence is also respected. Means multiplication and division for addition and subtraction. Here we have a demo of integer division. So 3 divided by 2 is 1. And we have white spaces that we need to ignore in the input. Same here, we have also white spaces. And this expression 5 divided by 2 is going to be 2 plus 3 is 5. So yeah, that checks out. Okay, cool. So I think there are different ways of how you can represent these computations. So for example, you can represent them as a graph structure. The challenge is then how to get a string like that into a graph. So this expression over there would start with a node of 3. Then we run into an operator, and that means we have to continue the expression on the right child of the operator. And now we run into a 2 node and another operator. That means we're going to have to put the operator as a right child of the plus operator, and then the 2 2's as the leaves of the multiplication operator node. And if you look close, you can see that this is basically the in-order traversal of exactly the input string, right? So if you know how to convert an in-order traversal into a binary tree, then you have solved the problem, because it's very easy to evaluate this tree structure. You know that every internal node is an operator node, and you just need to compute the result from the left subtree and then the result from the right subtree, and then combine these two results with the operator. So here, the result from the left subtree would just be 3. It's already a number. It's not an operator. And if we go into the right subtree, we encounter a multiplication operator node. That means we're going to get the results from the left subtree and the right subtree, combine them, becomes 4. So now I have a tree that has 3 plus 4 in it. We go back to the root and and then compute that. So that's one way to do it. And this will also be able to handle, like, if you have stuff like this. So you will be able to basically have, let's see, you will be able to build a computational tree for that, which would be 3 plus 2. And then you'd have the multiplication as the root, and this other 2 would be here, right? So that's the same thing. The parentheses change the operator order, I guess. That what is inside a parentheses has precedence over simple multiplication. So, and whatever has precedence will be closer towards the leaves of the node than to the root. So yeah, so that could be one approach to solve it. But I think here, because we have such a simple expression where we just have 4 different mathematical operations and just numbers that are positive or 0. I believe 0 counts as a positive number as well. We can, I guess, simplify it a lot for us. So, but one thing that we need to do is we need to pre-process the data, right? Otherwise, we're not going to know, okay, is this like a 1-digit number or a 3-digit or 2-digit number? Remember, the numbers can be large, right? So we need to be able to turn this string into a list of operators and numbers. That's the first task, I would say. And, you know, we could call it tokenization. So we tokenize it into numbers and operators. Tokenize, and that's the first thing we are going to do. And this would be an O of n operation because we need to go over all of the characters. And we need to store a result that has the same length as, or that has the length that is dependent on the length of the input string s. So tokenization will O of n time and O of n space. And then in the next step, we need to find a way of how we're going to evaluate this intelligently. But let's first do the first step. So we start with the tokenization. We need some kind of array that we're going to return in the end, right? And now we need to iterate over all of the characters, or character in S, I guess. So if our character is, well, the empty space, we're going to ignore that. If our character is an operator, so plus, minus, multiplication or division, then we just add that to our token list, right? Token, append, just a character. Now, the other case is if, well, actually, the only other case is that C is a digit. So what we have to do is we have to kind of, build up the number as you read it digit by digit. And there should be a known pattern to you how to do that. You find that in problems where you have to convert a decimal to binary and all this kind of stuff. Int digit. So this is actually, C is the digit. So that means here we're building up this number. Now, it is guaranteed, well, actually we have to init that number with 0 in the beginning. If we run into an operator, it means there was a number before, right? We cannot experience an operator without anything. And that is simply because we have no negative values. So we will never have a minus sign or a minus operator in front of a number without there being something else in front of that operator. So if we run into an operator, we know the previous token was actually a number. And in our case, that means we have been building up a number, but we haven't really added it to our token list. So we're going to do that. Append, so we're going to append the number, right? And we have to reset the number to 0 so that when we start encountering the next digits, we start building a new number from scratch. All right, so I think this would be our tokenization, except at the very end. The last digit, the last token in the string is also always a number. So we would have to add whatever number we've built up until that point at the end, very end again. Right, so that completes the tokenization. That's pretty much everything. I'm just thinking, yes, that should be everything. And because we are not using a string to rebuild the number string every time, this is not an O of n operation. This is n in the length of the string as. This is constant space that we need. So linear time, linear space overall. For storing the number, we only need constant space. So now we need to evaluate that list of tokens, right? And yeah, well, how are we going to do that? Well, that's a really good question. So we have to come up with it. So this is tokenize S, and then we return evaluate tokens. That's what we're going to do. Well, we know the edge case, right? So when tokens only contains one element, that's going to be a number. So if length tokens equals 1, return tokens 0. That's what we will return in that case. Now, if it's not 1, well, what do? Well, we now have to come up with a way to process all nice numbers. And I think the easiest way to do that is to, well, because we don't have any parentheses, we don't really need to build that the tree structure, right? So what we can do instead is, if we have 2 plus times 2, so all of those are tokens, we could just iterate through that list, and basically, as soon as we find like a multiplication or division, just evaluate that on the spot and write the result back into our list, and then we just continue, right? And even if there's now a division or something, let's say division by 2, we do the same thing. We just take the 4 and immediately divide it by 2 and write 2 back, and so forth. But we leave all the minus and the plus, whatever that might come there. But we eliminate all of the divisions and multiplications by evaluating them. And then we just have to do a final pass to add and subtract numbers in the end. So this simple structure of this expression makes this easier for us as well. Yeah, and that's exactly what we're going to do. So we need to actually, or we need to keep, I guess, we should probably be, well, I said we could insert in the original token list the results. We could, or we could build a new one. That would be a little bit cleaner, right? So, well, we're going to have an index that we'll use to iterate over all of the entries in the tokens list, So while index smaller than the length of the list of tokens, we are going to do something, and at the end of it, we're going to increment this. Now, if we were to build up, I think it's cleaner if we build up a new list. So how should we call this? Token reduce or temp, like a temporary. We could call this temp if we wanted to. Not tip. TMP for temporary. So what we now do is we basically have to, well, get the token from the list of the tokens at index. And now we check. Well, if token in multiplication or division, you can make a set or list out of that, doesn't matter, or just a string. It's constant time because it's a limited number of characters in here. If that is the case, well, then we know that the previous operand 1, is at tokens idx minus 1. We know that operand 2 is tokens at idx plus 1, right? And we could evaluate that right away. So we could say the result is, depending on what the token now is, if token equals multiplication, presses op1 times op2, and otherwise, if it's a division, it's the integer division, right? So if it's a division, it's that. Now we need to write back the result, right? So, well, how are we going to do that? We could use a temporary array for that, or we could write it into our original tokens list. The problem is that if we want to write, well, we should delete op1 and op2 including the operator itself, right? So we have 3 fields that we need to eliminate, and we need to write 1 back. Now, removing elements from the middle of an array is a linear time operation, so that's not very smart. But something that we can do is we could just say tokens at idx minus 1 is going to be equal to our result. And then we just say tokens at idx plus 0 is none. And at idx plus 1 is also none. So we're kind of marking them as deleted, I suppose. And we just need to make sure that we increase our value of idx. From our current, we have to skip over the operator 2. And in the loop, then we're going to increase this 1 more time to get to the next operator. So that is how we can do that, I believe. And now what we have to do is we have to do 1 more pass to evaluate all the pluses and the minuses. So that's pretty much what we will do. Just copy that. And what we do now is we iterate over the tokens. If token is in plus or minus, we do something. But also if token is none, just going to continue and ignore that. And we also need to take care of the previous index that was not none. Pref and idx are 0. Now if we run into plus or minus, we know that the operator is at the previous token position. And we also know that the next operator is at the next position because we always wrote it to the next one, right? So always directly let me think. Yeah, I think that is true. Because at idx minus 2, well, there could have been something else. But yeah, basically we have to remember the previous position where we had something. Let me think. That seems a little risky, even though if I might be on the right track. I think it would be better if we just build up a new array so that we don't have to deal with these edge cases that could be kind of really nasty. So instead of reusing the tokens array, we are going to build a new one. So instead of overwriting anything here, simply what we'll do is we'll just append res. We're just going to append the result value to our little thing here. And if the token is not in multiplication or division, we'll simply do a tmp.append token. Now that means we're writing the numbers into our TMP thing. So what we have to do is we have to get our ops tokens from TMP as well. So we will just pop them from the temp. So that would be the first operator. Then we would say, well, actually, to be honest, tmp.pop. Technically speaking, we would have to do this. tmp.append. The next token is going to be our next operator, right? And then we are going to immediately increment the idx because we want to skip over the token that we've just added. And then we pop out the operands in reverse order and push the result onto the stack, right? So that is exactly it. So now we've changed the implementation where we use TMP. We immediately compute the multiplication division before we add them to TMP. Otherwise, we just add the token. Cool. So now we're left with an array that, and we can do this. We're now going to assign this. So now we're going to iterate again through our little token list we're also going to have a new temp, because now we want to build up the results as well, the same way as we did before. We won't have none tokens anymore, so we don't need to take care of that. Else, we will only have tokens that are either a number or a plus or minus. So if we run into a number, we're just going to add it to our little temp stack, I guess. No, we should call this stack, really, to be honest. We should call the stack, yes, TMP stack, TMP, because we are only writing to the top of the stack and we're popping elements out of the top of the stack. So stack, 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 and yes, cool. And here we do exactly the same thing. We don't need previous anymore. The first operand is basically when we pop the previous element from the stack, right? Let me think. Oh, yeah, well, I'm stupid. So basically, in the second pass, it's very simple because we now have alternating numbers and plus or minus signs. That's all it is. So what we'll do now is we'll do while stack. We'll pop out operand number 2. Op2 equals stack.pop. Then we have the plus or minus as stack.pop. And then we pop out the first operand, stack.pop. So we're popping pairs of 3s from the stack, right? So in this example, we would pop 3 plus 4 from the stack. So 4 is the second operand that pops up, pop the first as the first, then the operand, and then the first operator. No, sorry. This is the operator. These are the operands that way. Cool. So now we're going to stack.append, well, op1 plus op2, pretty much, if op equals a plus, right? And if it's not a plus, it has to be a minus. It has to be a minus. And while length stack is larger than 1, because in the end we expect only one result to be on the top of the stack. So return stack.pop. That's what we will return. Evaluate, tokenize. So, okay. So let's simplify that a tiny little bit in terms of code. So, this video is actually quite long already, isn't it? So I'm very tempted to just skip over, doing the syntax checking, and let's just use the powers of the LeetCode gods to tell us what we typed wrong and what we did wrong. Here we're still using TMP. Obviously that can't work. TMP. EMP, do we still use that anywhere? No. All right, so I think, yeah, I'm tired. I'm just gonna hit run to see if there are any syntax errors. And we see one. So if token in multiplication or division. In string requires string as a left operand, not an int. So apparently, obviously, well, we have to first check if the token is a number or not, right? Because if we don't add a number, if we can make that a little simpler for us. So if the string version of the token is in that, then we're going to do the operation. Otherwise, string is going to be a number. We could also change num to be added as a string here if we wanted to, but that overcomplicates things, I think. So we do it like this. Oh, and we have to do it down. No, we don't have to do it down here. So yeah. that is pretty much it. And that seems to work for all of our test cases, which is nice. Test cases are the same ones that we see in the problem description. That's always the case in LeetCode. And now the big moment where we submit this and see if we've actually covered all of the edge cases or not. Well, okay, so there's another one. 1 minus 1 plus 1 returns minus 1 expected plus 1. So that's an interesting one. So we will have to walk through this one. So this one will be tokenized to 1 minus 1 plus 1. Yes. Now, if we evaluate this, the first token is, of course, a number. So string token is in something else. So we don't have any multiplication. So the first pass will not change anything. It will just append the token to the stack. Then when we go into the second part, we will pop off operator 2, the plus, and operator 1. And we have a plus. So what we'll do is we append the sum of 1 plus 1, which is 2. Aha. So here we see a little problem with the order of our evaluation. We should, because 1 plus 1 is 2, but we should really be evaluating it from the front, right? So that means we actually have to reverse our stack to be able to do that. So we could say stack equals stack dot. So yeah, so this is a logic error that we have. I think it should work now when we do that. What if we have 1 plus 1 minus 1? Well, then it should be positive 1 as well. Yeah, we're reading this backwards. That's the problem. We read 1 plus 1 minus 1 instead of 1 minus 1 plus 1. Yes. So let me test the test cases with this. Okay, that still works. Nice. Now if we submit this. Okay, so now we're getting 0 minus. Why is this not working? So this should go through the first parsing. Then we have 0 minus. Interesting. Okay, so I have to think about this. Why does that happen now? We have 0 minus. That's exactly how we get that as a string. But then we reverse the order, so we have that. We have 0. We have that minus. So actually, now the ordering is working against us, if I'm not mistaken. So, because we reverse the order, we also have to reverse the popping out of the operands. I think that's it. Let's try. So that works, right? And now we hit submit. All right, so there we have it. Okay, cool. So yes, so that's kind of tricky, isn't it, to get that to work? So you have to be really careful with that. I thought for a moment about the idea of maybe encoding the minus with the number that comes after that, but that wouldn't work. If we have 1 minus 2 times 2, that would be 1 plus minus 2 times 2. Well, actually, it probably would work. Yeah, that could be another approach where if the operator is a minus sign, replace it as a plus, and make the next number a negative one. Yeah, I think that could also work. Yeah, so, but yes, so the order in which we process these elements is important. And in our first pass, we actually, we pass from index 0 to the end. That's why that works. And then here we need to do the same. We can use the idea of a stack, but we have to reverse the elements to be able to pop them out from the end. Or otherwise, we just have to iterate over all of them like we did before. So maybe that's the better approach, where we just yeah, maybe we should implement that, because I think that would be the safer way. So idx equals 0, and then we do for while idx smaller than tokens, and here we just say tokens equals our stack. We could do that, or we just leave it at stack, but then maybe it's not a good description anymore if we leave it as stack. So it's tokens idx 0 and tokens is equal to stack. So now what we do is we say exactly the same thing as we do here. Right. So if we run into plus or minus, all we'll do is we just pull out the operands, and that's going to be even simpler than here. We just get then operand 1 is at, well, where is it? Tokens, idx minus 1. Operand 2 as token is idx plus 1. And let me think about this. Well, we still have to, well, we will have a result, I guess, right? Result equals 0. And in the end, we're going to return the result. Return result. So now if the operand is a multiplication or it's a division, we just operate, multiply our result with our operand 2 or times as division, integer division by operand. Well, op2. Well, result is always going to be op1, right? So that's what we're going to update. So if we run into a plus sign, that means we're going to, or minus sign, we're going to pull out the next index as the number. And our first operand is always the result. So all we need to do is we need to start at the result, and that is a stack at position 0, well, tokens. So what we do here is if idx equals 0, result equals token, and we're also going to, well, that's basically it. Right? Either index is 0 or the token is actually pointing to plus or minus. Those are the two cases, because as soon as we run to a plus or minus, we're going to pull out the next value and jump over the index with +1. Op is not defined. Did you mean? Oh, I see. So here we have token. Here we also have token. And mean op2? No, we didn't mean op2. Yes. Now test case 1 doesn't work. Okay, why does this now not work? Well, because we're multiplying, right? We're not adding. There's my plus sign, plus, minus. My brain is fried at this point, so that's why this happens. Okay, passes the test cases. Let's submit this. Okay, and that also works. So yeah, now that I've implemented this, I actually don't know which one I would prefer. With the stack version, you need to be careful that we actually don't use it like a stack, so we have to invert it first. Well, if you use it like a stack, we have to invert the list of the tokens. Otherwise, we're reading the equation from the wrong side. And the second way is also slightly tricky because you have to take care of how you initialize the result. And yeah, I mean, it's not as tricky, I suppose. But yeah, I guess it's a matter of taste which one you prefer. And I bet there's some LeetCode geniuses here who write the entire thing in 3 lines of code. But that's not really the point of a coding interview, right? You want to showcase your thinking, all that stuff. Even though I would say this was way too long for medium problem, I think it should be much faster. And I should have had, I guess, 5 errors less. At times I was tempted to start poking around to see what works. And that is not a good place to be during an interview. So yeah, but thanks again for watching. Hope you've enjoyed that one. And yeah, give those 2 implementations a try. It's a good practice.